All right, so among everyone here, I feel like I'm the odd person out because I'm here talking about education specifically. And what I'm working on is developing a course on exoplanets that's going to be used for teaching in-service teachers. And I'm doing this work with Chris Palma at Penn State. Ooh, fancy. So, our main goals for this entire project are to, one, teach these are going to be primarily late middle school and high school teachers, teach them about exoplanets, and to demonstrate good teaching pedagogy while we do so. So our course is designed, I'll tell you what all these terms mean later, don't worry, around what we call a coherent content storyline. The course is activity-based. It's not so much the teachers go through and read things. It's they're actually going to be doing things like their own little experiments. And to design those activities, we're using a framework that's known as claims evidence reasoning from McNeil and Kraychik. You can read about it in this actually book of theirs. And more importantly, we're going to make the inner workings of this course completely transparent to our student teachers. And we're going to make all the materials that we create for this course available online publicly to anyone who wants them. Only difference is if you take the course for credit, you actually get some credit for it. So, coherent content storyline is a way to organize a course. You start off with some underlying big idea. This is your goal for what you want to teach to people in the class. Usually you tie this to some phenomenon or some causal model. From there, you develop what we call your upper anchor. And this is, aside from just this big idea like saying exoplanets, you have to specifically lay out what your learning goals are for the class. From this point, once you figure out what your learning goals are, you have to go, okay, so if I want them to understand this, 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 and this, what do I have to teach them? And those are your course topics. Finally, from the course topics, you can then determine what the lessons and activities for the course are. Of course, there's a bit of a problem with this. As of now, we still don't have a single underlying theory that explains all of exoplanets. We have a bunch of things from different places that we've kind of mashed together. Have ideas from solar nebula theory, our ideas for models of stellar formation and how those stars evolve. We have the Nice model, which talks about how planets in our solar system didn't necessarily form where we find them now. In fact, Uranus and Neptune have switched places. Jupiter has moved in and then moved out. So planetary migrations are important to how these exoplanet systems form and how we observe them today. And of course, we have planetary evolution and atmospheric evolution if you want to get into things like habitability of these planets, which everyone here does, I'm sure. And it's one of those topics that is very important for people to understand when talking about exoplanets, because in large part it motivates our entire study of exoplanets. So as our central phenomenon, what we tie everything in the course back to, we're going to choose the Kepler orrery. Now this is not perfect, but what we want to demonstrate is the diversity present in exoplanet systems that we observe. So, of course, one thing you're missing from this is those really strange systems with very high eccentricity planets. But that's an addendum that we're going to say, okay, the Kepler orrery is great, all the planets we found here, but it's not complete, and here's why. Of course, the students are going to figure that out themselves as well. But it's going to be something that is explained pretty explicitly. The course activities are tied to these key points in the storyline. And this is basically, so this is our, laser? Okay. This is our upper anchor. And it reads that combining solar nebula theory with models of star formation predicts that planet formation is common in the Milky Way and can create planetary systems like our own, but also create systems that contain objects that do not exist inside our solar system. So this is including, we're looking for things like our own system, things with habitable planets, gas giants, potentially ice giants somewhere out there. But we also have things to explain like hot Jupiters, super Earths, mini Neptunes, and all of these things in totally weird places in their planetary systems compared to what we think of when we look at our own solar system. So to break this up, what we have to look at and teach them about is planet properties in our solar system. Give us an idea of how our solar system was formed. So we look at where the rocky planets are, where the gas planets are, where the ice planets are, and they give us an idea of the formation history of our solar system. Then they need to know about how we find exoplanets. The main things that we're going to be covering are the two biggest ones, radial velocity method and transit method, and then what these methods can tell us about these exoplanet systems and these exoplanets in general, because you don't get the same information from each. Radial velocity gives you things like mass, whereas transit gives you things like the size of the planet, and obviously a lot more than just that. Next, we want to hit them with the idea that planets are common within our galaxy. This is one of the biggest results out of the Kepler mission. Planets are literally everywhere, and we expect them to be everywhere. We expect every star to have at least one planet, on average, of course. Then, from there, start talking about interactions between these bodies. This is the stuff that, in our solar system, we know as the Nice model, but also gives rise to things like hot Jupiters. That the interactions between these objects in a system are important to that system's evolution. Finally, we want to talk about habitability. Once we've gone through all of these, we can start to get to the idea that under the right conditions, other planets may also host life. This, of course, is a big may, underlined, boldface, italics. You could probably increase the font size a bit as well. But it's one of the things that we really want to know and we really want to look for. So the activities themselves. The claims evidence reasoning framework, essentially, we're using it because it, one, teaches course material, and two, teaches the scientific practice. And both of these are incredibly important, in large part because we're targeting this at the middle school, high school audience, where a lot of the material that has to be covered and standards that have to be met are governed by NGSS. And NGSS actually puts huge emphasis on this scientific practices part. So the example I'm going to give you here is actually from a paper by Carrie Ann Rubin and the rest of the group in 2014. And it's using the example from a claims evidence reasoning activity with the question, how can the planets be grouped according to their properties? So students are given this question, they're given places they can look for the data, and they start investigating this. This class is broken up into groups, and each group, in this case, takes a different property and kind of classifies the planets by it. You may notice here that there aren't many numbers on this plot, and that's totally okay. This is a way of getting them to do quantitative reasoning that doesn't necessarily involve numbers. So they've broken things like the mass of the planets into size of like small, medium, and large. Or in the case of this guy right here, extra small. Then, after addressing each of these individually, the groups then bring their data together and then create a chart that looks something like this. Once they have this evidence collected and brought together, they start to develop and answer this question. They have the evidence. They need to make their claims based on that evidence. Part of this also is that they need to determine what evidence is relevant to the question. If we go back, we look at things like the tilt on the axis, and that's nowhere in their evidence that's listed here. So not everything is necessarily going to be relevant to what they're trying to figure out. Normally, or not necessarily normally, often there's a reasoning section that follows here. So I have claims and evidence. Well, what the heck's reasoning? So for this actual activity, there's no necessarily reasoning section, but generally what this will entail is that the students then, taking their claims evidence, have to figure out why that works. And that usually addresses some underlying phenomenon. In the case of one of the activities that I've developed is talking about radial velocity detections and how, or what properties you can determine about a planetary system from the radial velocity method. So the underlying phenomenon there would mostly be gravity. So they have to work through everything they see and come to some judgment about what is working here. Now for this particular activity, what we do is they go through these regular solar system objects And one of the things that they identify that you see here is that Pluto is in a completely different class from all the other planets. So we introduce them to the Kuiper Belt objects. And they start looking up this same data for all of those and come to the conclusion, they reach this completely on their own, I should mention, that Pluto belongs with all of these things instead of with the rest of the solar system. It's really, really cool to see. So that's all I have to say. I kept this talk short because most of you probably don't know that much about education. I assume there will be plenty of questions. So have at me.
I don't even have to ask anymore.
Hi, you're, first of all, not the only one. I'm actually applying to jobs in science education right now.
Awesome. Are you giving a talk on it?
No, I'm not.
There you go.
But I would love to talk with you more about that. One of the questions I have is, as you're developing this course, are you working with teachers and or actually trying to implement, like test this out in classes, currently or in the future?
So actually, once I've got everything developed, that's going to be done by the end of this summer. In the fall, we have a bunch of teacher volunteers that are going to be going through this. And then we're going to get feedback on that, evaluate what we have, probably tweak some things. But fundamentally, yes, we have to make this work for the teachers.
Great, thank you.
Hi, you're a very good speaker.
Well, thank you.
So this might be a controversial subject, but do you think you'll run into parents of students in middle school and high school that don't think exoplanets are a thing? And
mean,
that, like, you might...
It's entirely possible. It's not something I've considered, though. However,
I grew up in the South, so.
with any luck, fair. With any luck, the students will then be able to go home and tell their parents about what they're learning, and maybe from there, the parents may be, oh, so there is something else that could be out there. It's interesting, because a lot of what parents will be learning about exoplanets is probably going to be coming from their kids, because well, where else are you getting lessons about exoplanets? It's mostly in undergraduate education. So part of the goal of this is branching out further to move this knowledge lower down, so we start talking about it in high school and middle school, because it's one of those things that's just really cool. It's one way that a lot of people have gotten really interested in astronomy by thinking about where else could there be life, and then the consequences of everything from that on the astronomy side leading to studies of exoplanets. So I'd love to find out what happens with that. Hopefully I'll be done with my degree by then. And someone else can study that.
There was another one back here someplace. Yeah. Nope.
Really good talk. Good job. So in teaching, a lot of the emphasis nowadays, I feel like, is being placed on assessment. So are there tests? Are there quizzes? Is there self-assessment? Like, what's the best method of doing student assessment for how they achieve those goals? So in this case, so there's actually a course that's run at Penn State for teachers that does this already. But it's a different set of activities. It does use the solar system one. But the assessments in that generally tend to be, you know, kind of a wrap-up style paper on the particular experiments, the ones that are done in the full CER style, and just general notebooks and stuff like that, that they keep track of what they've done, what they're doing as well. So it's kind of an ongoing form of assessment that keeps track of, you know, you're not having them fill out tests or anything, but it's kind of a rubric-based system where you're following along with, okay, how are they being able to follow this? Are they doing this properly?
Any other questions? Oh.
I have a comment to the previous question, actually. So my advisor has been teaching a course called Extraterrestrial Life in Texas, Austin for probably 15, 16 years. And at TA for it last semester, more than 40% of students went into that class believing that creationism is as valid as evolution as a scientific theory. And I would say after a semester, the course went well, and it was a very heavy class, but the students learned a lot. So, yeah.
I'll also point out that you mentioned that was Texas specifically, and
work.
Pennsylvania at least does not have creation or anything similar in the standards for science education.
Okay.
It's also completely left out of NGSS. They've just like kicked it to the curb and said, no, we don't want this.
All right, we got to move on. Let's thank Diana again.